All right, today we're going to pull back the curtain on one of the most crucial but maybe least talked about parts of artificial intelligence, how a machine actually learns. It's a fantastic question, right? Because it's not magic, not at all. It's really a process of trial and error, a long journey to find the best possible answer. And the thing that guides that whole journey, that's something called an optimizer. Think of it like this, and I love this analogy. Imagine you're a hiker in a really thick, foggy valley. Your goal is to find the absolute lowest point. The optimizer, well, that's your strategy. It's the set of rules you're following to make sure every single step you take is a step downhill, getting you closer and closer to that solution. Okay, so let's dive in. Here's our roadmap for today. We're going to see how these strategies evolved from a really simple first step all the way to the incredibly powerful tools that we use today. So what's an optimizer's job, really? You can think of it as the engine of machine learning. Its whole purpose is to iteratively tweak a model's internal settings. Picture them as thousands of little digital knobs called weights and biases to reduce its loss. And loss is just a fancy word for error. It's pretty simple. The less error, the smarter the model gets. Our journey starts at the very beginning, with the original strategy. This is the foundation for everything that came after it, stochastic gradient descent, or as everyone calls it, SGD. SGD is just beautifully simple. It looks at a small piece of the problem, just one batch of data, figures out the absolute quickest way downhill from that exact spot, takes one small step, and then does it all over again, and again, and again, thousands of times. But there's a problem. Its path can be really jagged and inefficient, and because it's only looking at its immediate surroundings, it can get fooled. It can get stuck on these little bumps, thinking it's at the bottom, when it's actually just in a small ditch, what we call a local minimum. So how do we fix that? How do we stop it from getting stuck? Well, we give our hiker a boost. This is where momentum comes in. It's like giving that hiker a rolling ball upgrade. And here's the key difference. Instead of taking all these separate little steps, momentum acts like a rolling ball. It actually uses its history to build up speed on those long, consistent slopes. This makes the path way smoother, way faster, and it lets it power right over those small bumps that would have trapped SGD. Then things got even cleverer with Nesterov momentum. This version actually peeks ahead to see where the slope is going before it commits to the next move. This is brilliant because it can slow down earlier if the hill starts to flatten out, which stops it from overshooting the target and makes the whole journey even more direct. Okay, speed is great, but it isn't everything. What if the terrain itself is just tricky? With super steep parts and then really flat plains. This is where our hiker needs some new gear. This is the Smart Boots upgrade. This brings us to a whole new family of optimizers, Autograd, AdaDelta, and RMS Prop. Now, they all share one absolutely brilliant idea. What if the step size, what we call the learning rate, could change automatically depending on the terrain? And that's exactly what they do. They basically give our hikers smart boots that take small, careful steps when the ground is steep and treacherous, but then take long, confident strides when the terrain is flat and easy. This is incredibly useful for complex problems, especially with sparse data where some information needs much more careful exploration than others. So, we've got speed from momentum, and we have intelligence from these adaptive rates. So what happens when you smash them together? Well, you get the modern champion of optimizers. You get ADAM. It stands for Adaptive Momentum Estimation, and it really is the best of both worlds. It combines the speed and the obstacle-clearing power of that rolling ball with the intelligent, terrain-aware steps of the smart boots. And this, right here, is why ADAM is so popular. I mean, it's pretty much the default choice for most developers. It's fast, it's really robust, it handles huge data sets efficiently, and honestly, it just tends to work really well right out of the box for a massive variety of problems. So is ADAM always the best choice? Well, not necessarily. The crucial thing to remember is to think of these optimizers as a set of specialized tools, in a toolbox. There's just no single best optimizer that works for everything. You wouldn't use a hammer to turn a screw, right? In the same way, the perfect optimizer totally depends on the job at hand. So let's look at a quick cheat sheet to see how they all stack up. So this table really lays out the core trade-offs. You can see how something simple like SGD has its place. It's efficient, but it also has its pitfalls. And then you have more advanced ones like Atagrad, which are amazing for specific things like sparse data, but they can bring in new challenges. Even a powerhouse like Atom isn't a silver bullet. It might need some careful tuning to get the very best results. The key takeaway here is you gotta match the tool to the job. And that leaves us with a final thought. This journey of innovation is far from over. Atom is a fantastic default for now, but as AI models get bigger and way more complex, what new problems of speed, efficiency, and stability will the optimizers of tomorrow need to conquer? It's an exciting future. Thanks for watching.